Hello everyone. So today we are going to understand basics of MIMO. MIMO stands for multiple input and multiple output. In the earlier classes, we have discussed about NOMA and also discussed how NOMA can be used in VLC. Now we want to use MIMO and NOMA in VLC environment. So to understand MIMO, NOMA in VLC environment, we need to understand some basics of MIMO. So today we will discuss about multiple input and multiple output MIMO. So in RF, MIMO is used for increasing the reliability of the system, and this is achieved through diversity because there are multiple input and multiple output. So even if one link between one transmitter and another receiver is broken, there are other links available from where you can decode the information. So basically, there's a diversity there in the system and you are able to increase the reliability of the communication system. The second is there is several fold increase in data rate by transmitting information in parallel. So this is actually also called as spatial multiplexing. So these are the main uses of MIMO in RF systems. You increase the reliability through diversity, and also you get increase in data rate because you are able to transmit parallel information across different channels. So a typical MIMO system consists of multiple transmitters. So these are say there are T transmitters, and this is the channel here, wireless channel, and this is receiver, and these are receiving antennas. Assume there are receivers. The signal goes to this antenna, for example. It also goes to all the antennas. Similarly, signal from here goes to this antenna and this antenna. And there are many antennas. So we have assumed T transmitters, T transmitting antennas, and R receiving antennas. So the channel matrix which is formed, the channel matrix, is actually R cross T. And so H is R cross T, the dimensions here, and the noise is also getting added. So the equation, the system equation becomes Y. No, Y becomes a vector because there are multiple outputs. Is equal to channel matrix into X. X is again a vector because there are multiple inputs, plus noise, which is also a vector in each channel. So this channel matrix can be written as, it be R cross T matrix, start with H11, H1T, this will be HR1 and HRT. So basically H11 means receiver 1 and transmitter 1. So this is basically Hij. I stands for the receiver and J stands for transmitter. So the channel coefficient between jth transmitter and ith receiver. This is what Hij means. And these are the components of the channel matrix, coefficients of the channel matrix. Similarly, the noise, there are R receivers. So it will be a vector, N1, N2, so on and so forth, NR. So if you see the output, which is a vector, so Y1 for example, there will be R outputs, Y1 to Y2 to YR. So Y1 will be H11 X1 plus H12 X2 plus H1T XT plus N1. And similarly, you have Y2 and you can have YR. In a similar fashion, you can write YR. So there are actually various form of MIMO systems. One is very simple, which is single input, single output. So there is one transmitter and one receiver. The other is SIMO, that is single input and multiple output. So you have one transmitter and you have multiple receivers. This is RX1, this is say RX, and this is an example of a SIMO. And similarly, you have a MISO system, which is multiple input, single output. So you have multiple transmitters and single receiver. These are TX and this is RX. And MIMO, of course, has multiple inputs and multiple outputs. So now let us understand a MIMO channel. So suppose there is an input vector X, which has components X1 to XT. There are T transmitters. And Y, there are R receivers. So Y vector will be Y1, Y2 into YR. And Y is equal to H, which is a channel matrix. Will be given by Hx plus N. So this will be Y1 to YR, H1 to HR into X. So this is an example of a MISO system. So this will be actually a matrix here in case of MIMO. So in case of MIMO, H will be R cross T matrix. So for MISO system, that is multiple input and single output, this can be written as Y. This is H1 to HT. So let me again draw the MISO system, multiple inputs, and this is single receiver, and this is say H1, this is H2, this is HT, and this is data here is X1, This is xt here. So y is equal to h1 to ht into x into x1, x2, xt plus n. Now let us also understand the behavior of noise. What kind of noise is present in the MIMO system? So let us find out the covariance of noise. So for finding out the covariance of the noise, let us find out, because noise is a complex random process. So expected value of n into n Hermitian, this is Hermitian operator, is given by expected value of this. So this is n1 to nr, because there are receivers. So n, the components are n1 and 2 for each branch, into, then we have to take the transpose and then the complex. That is what the Hermitian operator means. So I have taken the complex and the transpose, gives me n1 complex, n1 conjugate, n2 conjugate and nr conjugate. So if you multiply this, you get expected value of n1 mod square, expected value of n1 into n2 conjugate, and so on and so forth. So expected value of n1 square is nothing but the noise, that is sigma n square, and other components are 0 because n1 and n2 are IIDs. n1 and n2 are IIDs. And expected value of is a zero mean process. So expected value of n1 is 0. Similarly, expected value of n2. So this can be broken down to expected value of n1 into expected value of n2 conjugate, which is actually 0. So what we get is 0. And what at the output we get sigma square IR. IR is the identity matrix of rank R or dimension R. So this actually tells me that the noise component are spatially coherent, because we are only talking currently and in the space direction, in the space dimension. Spatially coherent, spatially uncorrelated. So the value is actually, because it has only the diagonal components, so the noise across the receiver antennas is uncorrelated. So noise is spatially uncorrelated. Now let us introduce the time index and let us see what happens in the temporal domain or in the time domain. So this is the kth instant, y1 at the kth instant. So we have introduced the timing index here now. y2 at the kth instant and yr at the kth instant is given by this channel matrix for MIMO. This is x1 at the kth stand, x2 at the kth stand, instant, and then this is the noise n1 at the kth instant, and so on and so forth. So this equation introduces the timing part in the system model. And if I do the similar calculations as I had done earlier, when I was considering the only in the space domain, space dimension, and then if I do this and try to calculate expected value of n at the kth instant and expected value and the noise at the lth instant, this gives me sigma squared delta k minus L IR. So this has meaning, or this has value when k is equal to L, and it is 0 when k not equal to L. So we also conclude here that it is temporally uncorrelated also. The noise is temporally uncorrelated. So it is spatially uncorrelated as well as temporally uncorrelated. So we can finally conclude noise is spatio-temporally uncorrelated. So this is what we conclude about the noise, that it is spatio-temporally uncorrelated. Now let us discuss about the receiver part. So as we know, y is hx, this is again a vector here, and h is matrix here. x1 to xt, there are nodes, and y1 to yr, they are known because these are the outputs. So we know about the output and we want to decode about the input, which are unknown quantities. So we will use a receiver. So if r is equal to t, that is the number of receivers antennas and transmitter antennas are same, then we can always estimate the value of x. This is x estimate by simply taking the inverse of the channel matrix, H inverse Y. Because if R is equal to T, say square matrix, and inverse of a square matrix is possible. So we can estimate the value of X by taking the inverse and multiplying by the output. But if R is greater than T, then we have something like this. This is Y1K to YRK. This is a channel matrix, S1K, X2. These are the data symbols. If R greater than T, then H is not a square matrix, not a square matrix. And taking inverse of a square matrix is difficult. Sometimes it is not possible. So how do we handle such a situation when number of receivers are greater than the transmitters? R is equal to T, we can always solve. It's a square matrix, we can always find out the inverse. But it is difficult when R is greater than T. So for that, we use a technique where we choose the vector x, which minimizes the estimation error. Which is fx is equal to mod of y minus hx square should be minimum. And this is also called as least square error function. So we want to minimize fx, which is y minus hx. As you know, y is equal to hs matrix. So we want to minimize this function fx y minus hx. So we need to choose a vector x which will minimize this estimation error. So let us calculate the value of this fx. So y minus hx mod square can be written as y minus hx transpose into y minus hx. Right now I am assuming that h is not complex. If it is complex, then this transpose operator will be replaced by Hermitian operator. So in that case, I'll have to take the transpose and the conjugate. So right now I'm assuming this to be real. So now let us do multiplication of these two terms. So transpose operator is inside y transpose minus x transpose into h transpose. This order gets reversed when you take the transpose into y minus hx. Multiplying all the quantities, what we get is this equation, which is A here. And these are all vectors. So I have not put the sign here, but these are all vectors. For example, y is a vector, x is a vector, h is a matrix anyway. So y is a vector, x. So these are all vectors. Now vector difference, because I want to differentiate this fx with respect to x vector. So differentiation in vector is slightly different than what we are normally used to. So let me just briefly give an example of a vector differentiation. So vector differentiation, suppose there is a function gx, then the differentiation of gx with respect to x vector is given by partial derivative of gx with respect to the components of the x vector, which is x1, x2, and so on. So delta partial differentiation of gx with respect to x1, partial differentiation of x vector with respect to xt, and there are many terms in between. So let us take an example. Suppose there is a vector c which has component c1 to ct. Let gx be ct into x. So if I multiply with x vector, I get c1 x1 plus c2 x2 plus ct xt. Now if I take the vector differentiation, the differentiation with respect to x vector, what I get is c1 to ct, which is nothing but c vector. Also, I can prove this, that ct into x vector is equal to transpose x transpose into c. So this can also be proved. And if I take differentiation with respect to x vector for these two quantities, it always gives me a c vector. So basically we will use this and this to find out our earlier MIMO example, the estimate of x. So if I go to my earlier equation of this fx and I differentiate this equation A, differentiate this with respect to vector x, then I get 0 minus 2ht, these again vectors here, plus 2ht h into x vector. So let me just explain this again. So my fx was yt y minus 2xt ht y plus xt ht h x. So basically I have used this ctx, these are a vector, is equal to xt c which is nothing but c. So this will give me d by dx of, because this first term is 0 and the second term is 2hty, this is with respect to x, so this is minus 2hty. I am explaining the third term, The third term will be d by dx of this is xt, ht, h, x, and let us do it by parts. So this will be xt, so this is one part, this is another part, dxt by dx, ht, hx plus xt into d by dx of ht, hx. And this gives me ht, hx plus this will give me xt, ht, h, where I have used one of those earlier equations which I had discussed, which is actually this one I used here. So this gives me twice ht, hx. So where I have used the other equation, that is ct x is equal to xt c, and these are all vectors. So this is how I get this term. So minimizing the error, I need to differentiate with respect to x, which and equate to 0. So this will give me x estimate. So if I do this from here, I get ht h into x estimate is equal to ht y, and x estimate is given by this ht h whole inverse into ht y vector. Let me call this quantity as fzf, where zf stands for zero forcing. So fzf where zf is zero forcing. So here you notice this x is not, h is, I cannot get x estimate by simply taking inverse. So it is a different type of inverse here. So you see this function is ht minus 1 ht. So this is whole thing is the fzf, and this is called as not the exact inverse, the convention inverse in the conventional sense, but it is CDO inverse. So for estimating x, we need to have this operation on the channel matrix, that is ht into h inverse into ht, not simply h inverse y, because r and t dimensions are different, and it's a rectangular matrix which may not have a direct inverse. So we'll have to calculate fzf for getting the x estimate, which is also called as CDO inverse. Now let us see the properties of CDO inverse. For r greater than t, if I multiply this fzf by h in this way, then and I see that this is nothing but identity matrix of dimension t. Dimension t. And if I take the, it is not inverse, because if I take h fzf, this will be h ht h minus 1 ht, and this is not equivalent to it. So it is not actually inverse matrix in that sense, It is CDO inverse, because if I multiply H by this FZF matrix, I don't get identity matrix. So let's take a special case for R is equal to T. When it is a square matrix, it will be, for R is equal to T, for example, FZF will be HH, H minus 1 HH. So if I, because this is R is equal to T, that means the inverse of the matrix exists. So this will be H minus H inverse, H inverse, H. And this is 1. So this actually gives you H inverse. So with this, CDO matrix is applicable when R is greater than T, that is, number of receivers are more than the number of transmitting antennas, and when they are equal, this is simply H inverse. This is what we have seen here. So let us now take an example how to calculate how to estimate rather a signal where R and T are of different dimensions. So suppose there is a channel matrix which has a number of experiments have been done, and we have got this channel matrix. So first, for calculating the FZF, I need to have HH, H minus 1. This is whole is 1 into HH. So first let us calculate, because these are all real numbers, so it will be transpose, it will not be Hermitian. So H will be replaced by T. So HTH will be given by this, and if I take inverse of this is 1 by 17, and these are the elements. So the FZF, zero forcing matrix, will be given by this formula, whatever we have derived, and if you plug in all the values, this is what you get. So my estimate XZF, the X estimate will be for a zero forcing receiver, this is zero forcing receiver, will be FZF into Y. And I can write the different, for example, the X1 estimate will be minus 0.04, Y1 minus 0.17, Y2 plus 0.31, Y3, and similarly X2 will be 0.17, Y1 plus 0.27, Y2 minus 0.15, Y3. So there are 2 inputs and 3 outputs. So R is equal to 3 and T is equal to 2, which is a case of R greater than T. So these are the estimate values of X1 and X2 for a case where number of transmitting antennas and receiving antennas are not same. So let us understand what are the issues with the zero forcing receiver. Now, zero forcing receiver, let us understand, let us take an example of SISO system, single input, single output, where R is equal to T is equal to 1. There is only one transmitter, one receiver. Now, Y is given by HX plus N, where Y is the output, H is the channel coefficient, X is the input data plus noise. So if I take zero forcing, this will give me which is nothing but H inverse is equal to 1 by H. So X estimate for zero forcing is actually FZF. This is capital F into Y. And FZF we have calculated as 1 by h into y. Y is hx plus n. So if I multiply, I get x plus n by h. So if the channel coefficient, if the channel coefficient is tending to 0, this quantity actually goes to infinity. In other words, the noise gets amplified. Which is not a desirable solution. So how do we handle this this part, noise getting amplified? So let us also understand a little more about this noise getting going to infinity. So for example, as I had mentioned that my system, this is my xk, say, input, and then this is the channel matrix is, say, fz, and the noise is getting added here, and what I get is uk, and then on the other hand I have the inverse of the channel matrix fz, and this is, I get x estimate k. So this is our system diagram using zero forcing receiver. So, and suppose your noise, suppose your information is this. This is say information. And channel happens to be, say, like this. Channel has, so I'm deliberately showing h going to 0 at some place. Channel characteristics are given by this. So this is channel. And this is, say, noise. Then the equalizer or the inverse of fz, channel matrix, will be, because this is going to 0, so this will be going to infinity at this point. So this will go to infinity. So this is the characteristic of equalizer which I need to have at the input. And if I see my data, the recovered data, which is the information is this, and the noise component, because of this channel characteristic, it will go to 0 at this point, and then I will get something like this. This is the noise part. So this blows to infinity. So this is the noise part, goes to infinity. So there is a noise amplification happening. So this is the drawback of a zero forcing receiver. Whenever h is tending to 0 or close to 0, at that point the noise gets amplified. So it is able to remove the ISI completely, but there is a issue of noise amplification. So it removes the ISI, but there is an issue of noise amplification whenever the channel coefficient is tending to 0 or close to 0. So how do you solve such a problem so that the noise does not get amplified? So for that we use another receiver which is called as minimum mean square error. It is designed to minimize the error variance. To minimize the error variance. So basically, X estimate using MMSE minus X mod square, this expected value should be minimum. So this is the MMSE function. And we will not go into the details of calculation of estimate of X MMSE, but this can be done the way we have done for zero force receiver. So if you do all those calculations, then X estimate MMSE using minimum mean square error is given by this formula, where PD is the power in the data symbol, power in the data symbol, and H is the matrix, channel matrix, and I have used transpose here because I've been assuming that H is a real and it's not complex. If it is complex, then it will be replaced by Hermitian into PD HHT plus this is a noise identity matrix, total thing inverse by. And the same thing can be manipulated and can be written in a different form, which is PD into PD HHT plus sigma n square I, whole thing inverse HT Y. So both the expressions are equivalent. So let us understand how it is robust against noise. So Y is equal to Hx plus N. This is a simple case of a CISO system. So my S estimate will be given by PD H PD H square plus sigma square. So this is a case of MIMO system, but I am trying to explain this robustness against noise using a CISO system, where I have assumed there is one transmitter, one receiver, and it is defined by Y is equal to Hx plus N. So if I use a CISO system, then this expression X estimate MMSE reduces to PD H PD mod of S square plus sigma square Y. Now, if H is tending to 0 or equal to 0, so this quantity will be 0. But the whole thing does not go to infinity because there is a summation term here, sigma n square. So it does not go to infinity, even if H is tending to 0. So X estimate MMSE will be PD H into Y. This is 0, so this becomes divided by sigma n square. So it does not go to, the noise does not get amplified here. This can also be explained using earlier description, whatever we had used. So this is, suppose, your channel, and this is noise, this is say xk, this is nk, and you have the inverse of this, or MSC equalizer now here in this case, MSC minimum MMSC equalizer, and what you get is xk estimate. So suppose this is your info here, this is information and data information, and channel, let us see, it has a characteristic something like this, and this is a noise here. So the equalizer characteristic will be something like this. It will not go to infinity now. This is equalizer. This is the channel. It does not go to infinity, which is clear from this equation, because still there is a term sigma n square, so it does not go to blow up to infinity. And if you see the output, corresponding output will be so this is the info here. There is some, this is noise. So there is some ISI now introduced, but there is no noise enhancement. No noise enhancement. So MMSE is actually optimal detector, but it's quite complicated. So there is no noise enhancement, and improvement occurs at the cost of not totally removing the ISI. So it has some ISI, but you don't have any noise enhancement. So now let us see what happens at low and high SNR of MMSE receiver, minimum mean square error receiver. So basically we are doing some asymptotic analysis. When SNR is tending to infinity or low. So let us try to see this. Let us see at high SNR. So when high SNR, so this term, which is power square, signal power divided by noise, will tend to infinity, because the sigma n square is close to 0 in a high SNR condition. So if I put this value in the earlier equation which I had written for the when we were discussing the MMSE receiver, PD HTH plus sigma n square I is equal to PD HTH, because this is tending to 0. So we are left with only PD HTH. Now if you see the estimate, which was actually equation earlier, A, X estimate MMSC is given by this, and if I put this approximation, I get PD HT plus H, this is tending to 0, plus HTY into HTY. So this gives me, this PD will get cancelled. What I get is HTY, which is nothing but zero forcing receiver. So at high SNR, where PD by sigma n square tending to infinity, the estimate of MMSC receiver is nothing but zero forcing receiver. Now let us see what happens at low SNR. Low SNR means PD by sigma n square is tending to 0, because the noise component is very high, so this is tending to 0. Again, taking that equation, so this PD is very low because it's low SNR, so this quantity will be 0 in this case, and we are left with sigma n square IT. And if I plug in these values, this approximation in X estimate MMSC, what I get is PD sigma n square IT inverse minus HTY, or we can write this as PD divided by sigma n square HTY. And this is nothing but a match filter, where the impulse response is matched to the input. So this is nothing but match filter. So I can write this in a diagram form. So this is, for example, MIMO MMSC receiver. So there are two conditions which we have evaluated. One is high SNR and low SNR. So in this case, PD over sigma n square is tending to infinity, and in this case, PD over sigma n square is tending to 0. And we saw in high SNR, by putting this approximation, this MIMO MMSC receiver reduces to zero forcing receiver. And in case of low SNR, which is given in this slide, this reduces to a match filter receiver. Matched filter receiver. So in conclusion, MIMO receiver for zero forcing equalizer. So this is your channel here, this is the equalizer, and this is the estimated output. This is given the information part, and this is the channel which is tending to 0. And if you see the equalizer, this will blow up to the infinity, because there is a zero forcing receiver. So you can see here it is going to infinite, and this is the noise component. And at the output, information plus noise, this is your information, and the green part which is amplified, which is getting amplified at when the channel response is, when the channel coefficient is 0, is the noise part. So there is a noise enhancement which is happening in this case. And similarly for MMSE, this is your information. This is channel. Channel in this case is also going to 0 at some frequency. And this is the noise part. But because of that sigma n squared term coming in the denominator, it does not go to the infinity. So there is a limit here. So, and if you see both information and noise is given by this. So this part is the green one is the noise, and this is the data. So there is some sort of ISI which gets accumulated in MMSE receiver, but there is no enhancement, no noise enhancement. So that's the advantage you get using MMSE receiver. So this we will stop at this point. Now we have understood the MIMO concept, and we also seen the performance of MIMO using zero forcing receiver and MMSE receiver. So we'll use some of these receivers in our analysis when we discuss MIMO along with NOMA technique in VLC environment. Thank you.